That's what we're trying to find. And we know that that's true. Alright? Multiply both sides by BA inverse. So you'll get BA squared times BA inverse equals E times the same, BA inverse. Right? Now what's this? Well, it's just BA. Well, yeah, this just becomes BA, well, to the 2 to the minus 1. So that's just BA. And this is just BA inverse. So BA inverse equals BA. So it's, the inverse is the same. It's the same. So BA all inverse is just BA. How about this one? BA. It's just basically algebra, and you use the relations. Right? And why? You know, perhaps I should talk about the motivation. Why do all this kind of stuff? You need experience in you know, doing this kind of algebra so that you can fill in the group table for Dn, you know, for general n. You need to know how to play with this algebra. Okay, so B inverse A inverse. B inverse A inverse. I've forgotten from my head. Let me check the answers. Let me cheat. Professors can cheat. So, whoa, not tricky. Tricky. So this is I'm just taking this from the textbook. Now, in the text, the answers he just gives you this. Now, why is that true? So this is the same. That's the same. Oh, okay. Okay, I think I understand. Now look, yeah, he skipped a step. All right. Now, what is B inverse? Right? B squared's E, right? So the B inverse is just B. All right? B inverse is just B. Because B squared is E. All right. So here, instead of B inverse, he's just put B. In fact, he's skipped 2 steps. B inverse is just B. So just here, write B. But B is this. B is ABA. So he's gone 2 steps. B inverse goes B, and B becomes ABA. Right? So he's put that in there. And that gives you what? ABA. This is, well, he just says this is B squared, because that's just B. I don't know why he just didn't put a B in here directly. Okay, so B squared and A to the minus 2. Now B squared is just 1. So that's a to the minus 2, and the proof we had, it's just like this. A to the minus 2 is a to the minus 2e, which is equal to a to the minus 2, a to the n, right? Which is a to the n minus 2. So this is almost the same as this one. So a to the minus 2 is just a to n minus 2. There's your answer. Alright. This one. BA times BA squared. BA times BA squared. Now again, you've got this mixture of ABA, so let's use this somehow. So we can rewrite this a little bit. So that becomes ABA. A. Follow that? So I've just split this up into two A's. Now ABA is just B, so you'll get B squared A. But B squared is E, so that'll just leave you're just left with A. Okay, so that's done. Now, in the general context of your general dihedral group with n sides, regular polygon, n sides, you're to show this. So a to the I, and I is general, so it ranges from 0 to n minus 1. Okay, you're asked to show that. That's what question 3. So show that AI to B is equal to. You want to put. You're trying to bring the B to the left-hand side, okay? And you need that in your group table because it's usually expressed. When it involves a hedral, a flip. You want the B on the left-hand side. It's the format of the whole group table. So you either have A to some power, they're the rotation type entries in your group table, or you'll have B A to some power. Right? So if you have something like this, you want to be able to convert it to B something, where the B is on the left-hand side. So how to prove this? All right. Well, again, a trick. This is the same as AIBE. Okay, no change. But the E is this, A to the N. So that's AI, B, A to the N. Right. Now we can rewrite this again as AI, B, I times N minus I. Make sense? I've just split this up into two parts. Now why did I do that? Well, because then I get this kind of thing. We've met that before. Where? Here, yeah, this kind of thing. So we can knock down these A's progressively, step by step. We can knock down the power of these A's. Now, so this becomes A to the I minus 1, A, right, B, A, to the AI minus 1, A, N minus I, right? Now this ABA is just B, right, from here, one of your relations. So you'll get A to the I minus 1, B, A to the I minus 1, A to the N minus 1. Right? Now just keep doing that, and eventually eventually you'll get your eyes, these powers keep going down one at a time until eventually you just get ABA, right? ABA, and then A to the n minus I. But ABA again is just B. So B A to the n minus I. There it is. That's what you have to prove. Okay. Question 4. How many subgroups of order 2 in your general n-sided regular polygon dihedral group? How many subgroups of order 2? So both hedral type, flip type subgroups and rotation groups. Let's see. You'll have, now it's order 2, right? So you'll have the unit, you always have the unit, and it'll be some kind of flip operator. So how many of these do you have? Well, you have n of them. I think it's more subtle than that. I think it depends. I think the answer depends on whether your n is even or odd. Now, if it's odd, I think if it's odd, you'll have just n of these, right? These are your flip operations. So, look for each vertex, the next vertex, next vertex, so you have n vertices. So you'll have n of these flip operations. So the answer is n. Now, if you have an even number of sides, then you could also have a rotation. That makes sense. If you had an even number of sides, you could then rotate 180 degrees, right? It's a subgroup. So you could have you could have another one. You could have an extra one. And it always has the I, right? It's a subgroup. You could have something of this nature.